this video, we're going to be going over the Workstation.m script, which is basically a pre-processing hub for Raman spectra. Now, this script is divided into a few different sections, so we're going to go through all of them one by one, and I'll show you how they all work. First thing you want to make sure of, though, is to be connected to Carlton's VPN. Otherwise, any functions that make use of PLS Toolbox are not going to work. Now, the first section here contains global intermediate preprocessed spectra. So pretty much these variables store what your spectra look like at every stage in the preprocessing. So let's say you applied 10 different preprocessing steps and your 5th preprocessing step was background removal, and you wanted to see what your spectra look like right after background removal. Then all you have to do is plot this BGR right here. All of these correspond to different stages in the preprocessing. So CSR, for example, is for cosmic ray removed. SGF is Savitsky-Golay filter, and so on. We'll see what they all correspond to a bit later on. Next are the global preprocessing settings, and in here you'll find a few different parameters for different preprocessing functions. So you can change these parameters to whatever you want. For example, this is the SGF order and SGF window, which are the order and window size of the Savitsky-Golay filter. AVG num is the number of spectra to average if you're using shuffle averaging. And then snip window and snip order are the window size and order of the snip background removal algorithm. Next is the data importing section, and this is where I like to import my data. I made this function to make my life a little bit easier. It's called import data. And essentially what you do is you just enter a nickname, so kind of like a code name for a specific data set, and it will output the Raman shifts and respective data for that data set. So all these different nicknames you see here correspond to different data sets. So for example, Lysate Feb 2017-00 corresponds to our ocean optics data set. And if I were to enter this nickname right here into the input here, it would output the data from this data set. Now on your computer, this import data isn't going to work with all these nicknames here, because you'd have to change the directory of where your data is located. So if you want to use this import data, first of all, you just have to keep in mind that you have to be using this file structure, this data format for your data. So for example, in this data set right here, we have Raman shifts in the first row, and then all the numbers beneath the Raman shifts are intensities. And then in the first 3 columns, we have donor, dose, and serial number respectively. If you don't have this format, then the import data function isn't going to be very useful. So you can just use other data importing functions like DLM read or CSV read or load if you have your data in a .mat file. If we go into the import data function here, we'll see how it works. Essentially what you do is you input the nickname, and then it compares the nickname that you inputted to all these other nicknames here. And when it finds the one that matches, so for example, right now the nickname is Lysate Nov 2017T. When it finds a match, it changes the directory to where that data is located. And then it loads a mat file that I have that has the data stored on it. And then it uses this format data function, which I have at the bottom here, to extract the shifts from the data, so the Raman shifts, as well as the data itself. And what it also does is it trims the spectra to the specified fingerprint region. So in the case of this data set, the fingerprint region, so around 600 to 1800 wave numbers, is between columns 401 to 1601. So let's say you wanted to add your own data set into this function here. All you'd have to do is go to the end, copy this else if block, and then just paste it right underneath. And then for your nickname, you'll just want to change this line right here. So new nickname. The directory here in the CD function, you'll just have to change to wherever your data is located. So somewhere in your data folder, might have some new data. And then you want to load the .mat file with your data or your CSV file or whatever you're using. And then all you have to do is just change the column indices of where your fingerprint region is located. All right, so I'm going to get rid of this now. And we'll go back to our workstation.m file. Now, finally, we have the pre-processing section here. I have two different functions that allow you to pre-process your data. The first is the more general one that should work with any data set, and that's this apply function here. And next we have the prepset function, which works with data that's organized in the way that I was showing earlier. So Raman shift in the first row, intensities under those Raman shifts. And then in the first, second, and third column, we have donor, dose, and serial number, respectively. If your data is set up in that way, you can use the prepset function, and it'll make your life a little bit easier. First, we'll look at how to use the apply function since it's the most general. Now, in order to use the apply function, you want to input your data. So this only includes intensities. You don't want to include any spectral information like donor, dose, or serial number, as well as Raman shifts. You don't want to include those, just intensities. And in the second input, you want to specify a vector that indicates the pre-processing steps and the order in which you want to apply those pre-processing steps to your data. So really, this is just a row vector that contains numbers corresponding to all these pre-processing options we have here. So for example, if you input a 4, it'll apply an SNV correction to your data. And if you apply a 6 after that, then it'll apply outlier removal. So I'm just going to go through an example of how to use the apply function. First, I'm just going to run what we have so far. So as you can see on the right, it's created a bunch of variables. A lot of them are these global intermediate preprocessed spectra variables, but they're all empty because we haven't done any preprocessing yet. We also have these global preprocessing settings, so SGF order, SGF window, average number, SNP window, and SNP order. They all have values in our workspace here. And then finally, we imported this data set with this nickname right here, lysate nov 27T. So we got the shifts and the data from it. So if we open up shifts, we'll see we're looking at the Raman shifts from the data set. And if we open up the data variable here, we'll see that we have all the intensities as well as spectral information, donor, dose, and serial number. First of all, I just want to know what the two outputs here actually represent for the apply function. The first output is the preprocessed data, and the second output specifies the indices of rows that were removed from the data. So if you're using a function like outlier removal, some spectra are going to be removed from your data set, and removed is just going to tell you which rows were removed from the data input. So as an example, we'll try using the apply function to preprocess the donor 11 data in the data we just imported. So what I'm going to do is I'm going to output the preprocessed data into this preprocessed variable. And then the removed indices, I'll just keep it in a variable called removed. And we'll set that equal to apply. And here we want to enter our data set. So I'm going to write data. Now, since we're using the apply function, we only want to be inputting Raman intensities, not spectral information or anything else. So when we go into the data set here, we'll see that our intensities are located in columns 4 till the end. And for donor 11, we only want rows 22 till 13, 12. So I'll extract those rows and those columns. And then in the next input of the apply function, I'm going to just specify which pre-processing options I want to apply. So these are the ones I typically apply to my data. I just have them set here so I can remember. I'm going to copy and paste those. So essentially what's going to happen is that it's going to take the data that we just specified here, and it's going to apply operation 6, which is outlier removal first. And then cosmic ray removal, operation 8, which is shuffle averaging, option 2, which is Savitsky-Golay smoothing, 4, which is SNV correction, 5, which is background removal, 6, which is outlier removal, and 7, which is normalization. Vector normalization to be specific. So finally, I'm just going to add a semicolon there. And if we run the data, we'll see that our workspace has updated. We now have our pre-processed spectra in the pre-processed variable here. So that's what that looks like. And we can also check the indices of rows that were removed from the original data set in this removed variable that we created. So this is just a cell array. In the first entry here, it contains the indices that were removed in the first application of outlier removal. So that would be this case right here. And then in the second entry in the cell array, it would contain the indices of removed rows from the second application of outlier removal. In this case, though, it seems like there weren't any outliers, so it didn't remove anything in the second application. If we want now, we can plot our data and see what it looks like before and after. So I'm going to plot shifts first, and then data. Extract the donor 11 data from our data set, and just hit enter. And this is what we get. So we have a bunch of outlier spectra here. We have some outlier spectra at the bottom. You can see a few cosmic rays here. And yeah, so after pre-processing, our data looks like this. So you can see our plot updated, and we're now looking at our pre-processed spectra. And as you can see, there's a lot less variation, and the spectra are a lot cleaner now. Now let's say we wanted to see what our spectra looked like after SNV correction. So that was option 4 right here. All we have to do is go to our global intermediate preprocessed spectra, find which variable corresponds to SNV correction. So that would be this one, SNV, and we just have to plot that. So I'll plot shifts and SNV. And when I open our plot, we'll see that is updated again. And now it's showing us what the spectra look like after first applying outlier removal, then cosmic ray removal, shuffle averaging, Savitsky-Golay smoothing, and then SNV correction. We can try pre-processing the spectra again using different parameters. So for example, we can try changing the Savitsky-Golay filter window size to something really big like 51. Once it's done running, we can plot our pre-processed spectra. And let's just bring it over, and we can see what it looks like now with a Savitsky-Golay filter window size of 51 as opposed to what we had earlier, which was 11. So obviously this isn't very representative of Raman spectra, so I'm going to change this back to 11. But that's just showing you how you can mess with the pre-processing settings here and see how they affect your spectra. Now that we've looked at how to use the apply function, I'll go over quickly how to use the prepset function here, which is similar but makes your life a little bit easier if your data is set up in this particular format here. So first, let's look at the inputs and outputs of the prepset function. The first input here is your data. Unlike the apply function, you want your data here to include spectral information such as donor, dose, and serial number. The second, third, and fourth inputs here are just row vectors that specify which donors, which doses, and which serial numbers you want to include in the pre-processing. And finally, we have the pre-processing input here at the very end, and it's the exact same as the operations input from the apply function. All you have to do is just input some row vector that contains a bunch of pre-processing steps, and it'll apply all of those one by one. Next, we can look at the outputs we have. So the first output, this all right here, contains all of your pre-processed spectra. And then the train and test variables contain 70 and 30% of of the data respectively. So this is just if you want to build a discrimination model, for example, and you want to train it with 70% of your data and then test it with the remaining 30% of your data, you can use these two variables instead. And the way it splits the data up is that, so in both train and test, there is an equal proportion of all the doses. So there's an equal representation of doses in both sets. So it's not biased to any particular dose. Let's look at how this works in action. So I'm going to output my pre-processed spectra, as well as a train set and a test set. I'm going to call the prepset function. I'm going to input my data. So again, has to include the first three columns here. And then for donor, I'm going to grab donor 11 and donor 17, for example. So to do that, I'll just specify donor 11 and donor 17 in this row vector here. In the next input, I want to specify the doses. So I want to grab doses 0 and 5. For the next input, we have serial number. In this case, I want all of the spectra from donor 11 and donor 17, 0 gray and 5 gray. So if you ever want to grab all the donors or all the doses or all the serial numbers, then you just have to input a -1 in the respective input of the function. Finally, for pre-processing, I'll just use the same pre-processing that I used before. Just copy and paste that into here. And then let's run the function. Once it's done, we can head over to our pre-process variable here. We can look at the data that has been pre-processed. It now still contains the spectral information such as donor, dose, and serial number. Now there are a few things to notice. First of all the doses have been added with a 1. So for example, all these 1s here are actually 0 gray, but 0 plus 1 is 1, so that's why we have a 1 in the second column here for 0 gray. And then all these 6s are actually 5 gray. And the reason I do this is PLS Toolbox interprets any spectra with a 0 as an unknown class when you're trying to do something like PLSDA. So obviously, in our case, 0 gray is not actually an unknown spectra. It's we know it's 0 gray, so we don't want it to think that it's unknown. So I just added a +1 to everything, and just have to be careful to remember that all these spectra are actually 0 gray, all the 6s are 5 gray. And for example, if you had 2 gray or 1 gray spectra in your data, then the 1 gray would become a 2 in the second column, and the 2 gray would become a 3 in the second column. Next, we will notice that we grabbed all the 0 gray and 5 gray spectra from donor 11 and donor 17, which is exactly what we wanted. And then in the third column, where we usually have serial number, which indicates kind of the order of the measurement, all the numbers have been replaced with 999. And the reason for that is because we applied shuffle averaging. So that's this 8 here. 8 corresponds to shuffle averaging. And when you're averaging data, the order in which the data was taken doesn't really make sense anymore. So I just change all these to 999. Another thing to note is that the function actually goes to each donor dose pair and applies the pre-processing individually to all of those pairs. So for example, this function here will start with donor 11 dose 0 and apply all the pre-processing. And then it'll go to donor 11 dose 5, apply all the pre-processing to that set of data. And then it'll switch over to donor 17 dose 0, apply all the pre-processing on that set of data, and finally end it by applying the pre-processing to donor 17 dose 5. And the reason for that is simply some of these pre-processing methods just don't make sense to apply to all the data at once. So for example, you don't want to be averaging 0 gray and 5 gray spectra together, because those are supposed to look different, and if you start mixing them together, you're not going to be able to discriminate between the two. Another example would be outlier removal. So let's say, for example, most of your spectra happen to be 5 gray and the rest were 0 gray. Then it might consider the zero gray samples to be outliers and start removing some of the zero gray samples, which we don't want. Obviously, the zero gray samples themselves are not outliers. We want them all in the data set. The only outliers we want removed are those that are actually behaving differently from all the zero gray and all the 5 gray spectra. Again, we can look at what our preprocessed spectra look like just by plotting them out. So I'm going to plot shifts against preprocessed. I just want to be careful to not include the first 3 columns from the preprocessed variable, because now it includes donor, dose, and serial number. So I'm going to include all rows here, but just take the intensities from the 4th to final column. When I hit plot, we get this plot, and it shows us what our preprocessed spectra look like. Again, we can compare to what our spectra look like early on in the preprocessing chain. So for example, if we want to compare to what our spectra looked like at the cosmic ray removal stage, all we have to do is create a new figure and plot shifts against CSR, which stands for cosmic ray removed. So I'll bring that over. And if we change over to the other figure as well, we could see a before and after. If all you wanted to do was just pick out some donors and doses and not apply any preprocessing at all you'd have to do is enter an empty array here. To finish off, I just want to quickly go over how this apply function actually works and what it looks like. So if we go in, we're going to see all these global intermediate preprocessed spectra, as I showed before, as well as different preprocessing parameters, which we gave values to in this section of the code. And then down in this for loop block, we have the area where the actual preprocessing is being applied to the data. So your data gets put into this current variable, and then what happens is whatever preprocessing step you're on, it inputs the current variable as the input for the preprocessing, and it also outputs the current variable as the output of the preprocessing. So that way it lets you actually apply as much preprocessing as you want in whatever order you want, and it just makes things pretty convenient. Let's say you had another preprocessing method you wanted to add to this function here. All you'd have to do is copy this else if block here, paste it just underneath, increase the number here to whatever's next, so it would be 10. And then in here, you want to just replace this line of code with current equals and then whatever function contains your preprocessing, and then input the current as the data for that preprocessing step. So let's say, for example, you wanted to change this to something that takes the mean of the spectra, then you can just change this to mean. And then finally, you would just have to change this global variable here to something else. So mean spectra, you can change it to that. Set it equal to current. And then all you'd have to do is go to the top of the function here, add that variable to the end, and then go to the top of the workstation and add the variable again into this global variables line here. And after you do that, you can just add that step here so you remember what number corresponds to that preprocessing step. And then all you need to do to use it is to just include it in your preprocessing row vector whenever you're using prepset or apply. So that was an overview of how to use the workstation, and I hope it was helpful.